Hello, folks. Welcome back to our conversation about Gibbs free energy. And in this video, we are going to look at how we can find the Gibbs free energy for a reaction that is at non-standard conditions. So this is what we're going to use when we think about a reaction trying to achieve equilibrium. So let's remind ourselves about what it means to be at standard state conditions, what that means for a state of equilibrium, and then how we might deviate from that state of equilibrium and how we might express that then change in free energy as a result. So standard conditions or standard state conditions, reminder, delta G with this little knot, so delta G naught reaction, and just like we saw with our enthalpy and entropy terms, these are things that have been determined under standard state conditions. So a reminder, standard state conditions, this is one of the assumptions we made, is that unless otherwise stated, we're operating under standard state conditions. So if we have a gaseous substance, they have a pressure of 1 bar. We are looking at pure liquids and pure solids. 1 mole of them. The solutions that we consider are at a temperature, or sorry, a molarity of 1.0 molar. And the temperature for standard state condition is 25 degrees or 298 Kelvin. So let's look at how these conditions may or may not be applicable to a system that achieves equilibrium. So question, for a reaction that undergoes some kind of change to achieve equilibrium, is that change performed at standard state or standard conditions and in our standard states? So if we're thinking about like all the gaseous reactions that we looked at that react to form products and establish an equilibrium using Kp to describe that equilibrium, we were not at 1 bar of pressure, right? We looked at various different pressures. This one here, I think, is the big tip, right? Anytime we talked about reactions happening in solution or aqueous reactions, our concentrations were not always 1 molar, especially once we got to equilibrium. And then if we think about like the reactions we've had here, this has not always been 1 mole of pure solid liquid, and we've even seen temperature deviations. So at equilibrium, recall that the standard change in Gibbs free energy is equal to negative RT ln K. This is from our previous video, where R is 8.314 joules per mole Kelvin. It's our gas constant. T is the temperature in Kelvin, and then K is the equilibrium constant. But again, this is once we have hit as a chemical reaction the point of achieving equilibrium. And we're assuming that we're achieving equilibrium in standard states, right? So there's got to be a way for us to account for like the reality of these reactions that we perform energetically, right? They are not at standard conditions. or in their standard states. So let's talk about how we might create like a little adjustment to how we calculate delta G. So let's go ahead and let delta G reaction be the change in free energy of a reaction that is not at its standard state conditions So let's think about how we might express this. We saw that there was this exponential relationship here between change in Gibbs free energy and a system's at equilibrium, its equilibrium constant. How would that be affected if we were not at standard state? So instead of relating to our equilibrium constant K, we are going to relate the Gibbs free energy to Q, the reaction quotient. So we have this equation here, delta G reaction. So our change in free energy not at standard state conditions is equal to whatever our standard state conditions were when we were at equilibrium, plus, oops, sorry, not when you were at equilibrium, just at standard state. There we go. Plus RTLN Q. So what does this do for us if we are thinking about a system that is not at equilibrium that then tries to achieve equilibrium? So we are going to look at this diagram over here and think about what happens if Q is equal to K, if Q is less than K, and if Q is greater than K. So let's see here, Q is equal to K, that is this scenario here. So if we are looking at the state of how Gibbs free energy changes, G, against the reaction progress, where we call this middle state here the lowest or 0 point energy of the reaction to be where we're at equilibrium, then if we are at a reaction quotient that is equal to K, we are at equilibrium. So then we can say that delta G reaction is equal to negative RTLNK because delta G reaction has to be equal to 0. We have this thermodynamic reversibility once we've achieved our state of equilibrium, if we're talking about very, very, very infinitesimally small changes in energy input and output, free energy input and output. All right, what if K is less than, or sorry, Q is less than K? So that would be looking at let's see here. Here. So Q is less than K, then what we see is in order for us to be at equilibrium state here. So Q, oh, I think I had this identified as the wrong one. So here, if Q is less than K, then we have concentration of product to the X over concentration reactant to the Y. This is going to be larger, and this is going to be smaller. So we expect a shift right to achieve equilibrium. So if we are going to shift right to achieve equilibrium, then we are going to have this term be smaller, which in effect is going to cause this term to be greater. So we're going to have to shift right. Where's my color? This is a rightward shift. And we're looking at which graph here? Let's see here. So this is our equilibrium state. All right, in order for us to achieve this shift right, we have to then increase the amount of reactants and then decrease the amount of products. So that means that we need to take free energy away from the products and go back to forming reactants. So if we've got delta G product smaller, let's see here, that means delta G reactant has to be bigger here. It would be this graph here. Okay. So this would be spontaneous, because we are going to take some of the free energy where we're shifted off from our reactant to products and use it to back reform reactant from product. Which would mean that, looking at if Q is greater than K, here's our equilibrium state. This is going to be the exact opposite of that. So we would see non-spontaneous with delta G greater than 0, meaning that in order to achieve equilibrium from where we are in this reaction quotient, which is where concentration of products, let's do black, the X over concentration reactant to the Y, this is larger and this is smaller. This is going to affect some kind of shift left if we're going to try to achieve equilibrium. So we're going to try to take away from product and make reactant. Here we go. And here we're going to try to take away reactant, make product, right? So take away from reactant, go down, make product. Take away from product, go down, remake reactant. And then here we have delta G is equal to 0, lastly. Okay, so it is through a comparison of Q and K that we can understand how our change in standard free energy is going to be affected. It's either going to be raised or lowered, right? So like if Q is smaller than K and is fractional, right, that would give us a negative number. So that would mean that this decreases. If Q is larger than K, meaning like, let's say it's non-fractional, then that would be a bigger number here, which would make this an increase here. So this would increase. So let's see here. Let's make this not Q equal to K. Let's do Q less than 1 and Q greater than 1. Okay. So in our next slide, we're going to actually practice this. Like we're going to use this equation here to see if we can't determine how the equilibrium of a reaction at non-standard states can be calculated, meaning specifically its free energy of this reaction. So this is the free energy. In a reaction occurring at non-standard states and non-standard conditions. So we will apply this equation in our next video, where we look at an actual chemical reaction that tries to react and then achieve some equilibrium by comparing like what's going on before the reaction and looking at how that compares to K, thinking about what are we going to need to do in terms of who's going to have to take energy from what, right? Where in our system versus our like surroundings are we going to need to have free energy exchange? All right, next video coming up.